In the past few lectures, 2 lectures, we have discussed the basic phenomenon behind the development of quantum mechanics, namely the wave particle duality. And then we continued our discussions to understand the Dirac delta function. We will continue on discussions on the Dirac delta function, and we will introduce Fourier transform of a function. However, before we do that, I thought I will give you a list of references. There are a large number of books written on quantum mechanics, but some of the extremely good ones are listed below, are listed on this slide. The first one is of course Professor Dirac's book. It is a classic on principles of quantum mechanics, published by Oxford University Press. And then we have the famous Feynman lectures on physics, volume 3. The first few chapters discuss the wave particle duality and the uncertainty principle in a very beautiful way. I would advise all students to go through the first few chapters of the book. And then there is a book, a classic, a very nicely written textbook by Leboff on introductory quantum mechanics. And then there is a book by Townsend, a modern approach to quantum mechanics, published by McGraw-Hill. And for the history of the development of quantum mechanics, there is a very nice book written by Max Jammer entitled The Conceptual Development of Quantum Mechanics. I will be following our own book, which is entitled Quantum Mechanics Theory and Applications. It is currently in its 5th edition, and it has been published by Macmillan India in New Delhi, and also the 5th edition has been reprinted by Kluwer Academic Publishers in Dordrecht. There is another book that I have written, a very thin, a thin book, which is entitled Basic Quantum Mechanics, and which includes a CD. We have developed a software which we will demonstrate in the next few lectures, and it has also been published by Macmillan India, and the paperback edition now contains the CD. So, as I mentioned earlier, we will continue our discussion on the Dirac delta function, and we will introduce Fourier transforms, which plays an extremely important role in the development of quantum mechanics. We had given one of the representation of the Dirac delta function in terms of a rectangle function. Here the rectangle function is such that its value is 1 over 2 sigma, and then 0 beyond 2 minus sigma and 2 plus sigma. So that as the value of sigma becomes smaller and smaller, the width of the rectangle becomes smaller and smaller, the height becomes larger, but the area under the rectangle always remains unity. This is perhaps the most straightforward, the simplest definition, representation of the Dirac delta function, and we define and we write, this is one of the representations, delta of x minus a as the limit of the rectangle function in the limit of sigma tending to 0. When sigma tends to 0, the width of the rectangle becomes extremely small, the height becomes extremely large, but the area under the curve remains unity. And because of this property, the delta function is such that if I integrate the delta function with multiplied by an arbitrary but well behaved function f of x, then it picks up its value only at the point x is equal to a. And we define the Dirac delta function through these two equations. Delta of x minus a is 0 for x not equal to a. At x equal to a, it is not defined, actually it has an infinite value, but we represent the function by a spike of unit height. This is how a Dirac delta function is represented, and it is defined by these two equations. We next consider the Gaussian function, and the Gaussian function is, we define as such that g sigma of x is equal to 1 over sigma under root of 2 pi e to the power of minus x square by 2 sigma square. Now, this integral we had derived last time, and we will be using this very frequently. E to the power of minus alpha x square plus beta x dx is equal to pi by alpha e to the power of beta square by 4 alpha. The limits, all limits are from minus infinity to plus infinity. So, if I substitute, if I now write down the integral of g sigma of x, the Gaussian function, g sigma of x dx, then it will be, I will have 1 over sigma by root 2 pi outside, and then minus infinity to plus infinity e to the power of minus x square by 2 sigma square dx. If I compare the integrand, this integrand with this integrand, we find that alpha is equal to 1 over 2 sigma square and beta is 0. So, therefore, this will become, the integral will be 1 over sigma under root of 2 pi under root of pi alpha, that is pi divided by alpha. So, 1 over alpha is 1 over 2 sigma square. So, this is 2 sigma square, and then e to the power of beta square, beta is 0. So, this factor becomes 1. So, as you can see, the 2 pi cancels out, under root of sigma square is sigma. So, this is equal to 1. So, therefore, this integral g sigma of x dx is equal to 1, is unity. The area under the curve is unity for all values of sigma. So, let me plot this function. Let me plot this function, this g sigma of x that I have written down, and of course, sigma is greater than 0. Sigma is greater than 0. So, if you plot this, you will find that if I take sigma is equal to 1, then it will have a width something like this. This is a Gaussian function, and this width is of the order of sigma. This is something like the full width at half maximum. If this value is 1, if we take this, the peak value as 1, then the full width at half maximum is about sigma, maybe square root of 2 sigma or 1.5 sigma or something like that. Now, as I make the area under the curve, I have just now shown to be unity. So, as I make sigma smaller, because of the factor of 1 over sigma, the value of the function at x is equal to 0 becomes smaller and smaller, larger and larger, and the width becomes smaller and smaller, but the area under the integral, area under the curve remains unity. So, therefore, it has all the properties of the delta function, and so therefore, we can write that limit of sigma tending to 0, the g sigma of x, that is 1 over sigma under root of 2 pi e to the power of minus x square by 2 sigma square. This is a yet another representation of the Dirac delta function. So, this is a delta function centered at x is equal to 0. If I want to displace the curve, if I want to shift the origin by a, so therefore, we can write delta of x minus a is equal to limit of sigma tending to 0 1 over sigma under root of 2 pi e to the power of minus x minus a whole square by 2 sigma square. This is known as the Gaussian representation of the Dirac delta function. So, here on this slide we have shown that the function g sigma of x, I define this as 1 over sigma under root of 2 pi and plot, and in the figure below we have plotted this function for sigma is equal to 0.1, 0.2 and 0.4. So, the width of the function is of the order of sigma, and as the value of sigma becomes smaller and smaller, the width becomes smaller and smaller, the localization of the wave function becomes smaller and smaller, and the height becomes larger and larger. But the area under the curve is always unity. So, we have what is known as the Gaussian representation of the Dirac delta function. So, this is an important representation of the Dirac delta function, but there are many representations of the Dirac delta function. This is yet one more representation. Now, we will consider yet another representation of the Dirac delta function, and that is known as the integral representation of the delta function. So, let me do it carefully. There is a function, there is an integral, definite integral, which is equal to minus infinity to plus infinity sin g x divided by x, the whole thing divided by x. So, this is a sinc function, something like that, and integral this is equal to pi for any value of g. We assume g to be greater than 0. For any value of g, the evaluation of this is extremely straightforward using Laplace transform technique and is given in almost all books on mathematical physics. But the thing that I would like to emphasize is sin g x by x dx is equal to pi. So, I write this as minus infinity to plus infinity sin g x by pi x dx is equal to 1. If I plot this function, you will find that sin g x over pi x in the limit of x tending to 0, the numerator becomes g x and the denominator becomes pi x. So, this becomes g by pi. And as you can see, the first 0 of this function occurs at g x is equal to pi. In fact, the zeros of the function occurs at g x is equal to pi, 2 pi, 3 pi, 4 pi, minus 2 pi, etc. So, if you plot this function, you will find that the value of the function, let us suppose g is 1. So, g is 1, so 1 over pi is 0.3, so something like this, and the first 0 will occur if g is 1 at x is equal to pi. So, something like this. So, this is a damped sine curve, and it will be symmetric on the other side. So, it will be something like that. If the value of g is increased, then let us suppose g becomes 10. So, this value increases by a factor of 10, I cannot show you on this, but it becomes, and then the first 0 occurs at x is equal to pi by 10, if g is 10. So, therefore, it becomes very sharply peaked, and it becomes like this. But the area under the curve remains unity. So, therefore, we have yet another representation of the Dirac delta function, that limit as g tends to infinity, sin g x by pi x has therefore all the properties of the Dirac delta function, and I can write this as delta x. So, so I will use this representation. Now, let me write down what is sin g x by pi x. If I integrate a function like this 1 over 2 pi, let us suppose from minus g, consider the definite integral minus g to plus g e to the power of plus I k x or minus I k x, it does not matter, multiplied by d k. So, I carry out the integration over k and the function is e to the power of I k x. The integral is trivial, is very simple, 1 over 2 pi, and if I integrate this with respect to k, so I get e to the power of I k x divided by I x from minus g to plus g. So, you will have 1 over 2 pi, 1 over 2 pi, and I x will in the denominator, let me put x outside, I here, e to the power of I, k becomes g. So, I g x minus e to the power of minus I g x. I multiply by 2 and divide by 2. So, this quantity e to the power of I g x minus I g x, this quantity is just sin g x, as you will appreciate. So, this becomes 1 over pi x sin g x. So, therefore, sin g x over pi x, this quantity is just this integral, and so therefore, we have a very important relation. We have just now shown that sin g x over pi x, let me leave some space, this is equal to 1 over 2 pi minus g to plus g e to the power of I k x d k. Okay. So, this I have shown just now by evaluating the integral on the right hand side, and this follows immediately. But I have just now shown before that, that in the limit of g tending to infinity, this becomes the Dirac delta function, delta of x. So, if I make limit as g tends to infinity, so this becomes 1 over 2 pi minus g to plus g. Actually, you can take either plus sign or minus sign, it does not really matter, plus minus I k x d k. So, this is known as the integral representation of the Dirac delta function. This is known as the integral representation of the Dirac delta function, So, if I shift the origin, if I replace x by x minus x prime, so I get delta of x minus x prime, this is equal to 1 over 2 pi, sorry, this because I have put g equal to infinity, I am sorry, this should be minus infinity to plus infinity. So, you will have, because if I make g tend to infinity, this becomes minus infinity to plus infinity. So, I should have included that minus infinity to plus infinity e to the power of either a plus sign or a minus sign, it does not really matter, either one, e to the power of I k x minus x prime d k. This equation is an extremely important equation. It is known as the integral representation of the Dirac delta function, integral representation of the Dirac delta function. So, let me show this in the form of slide, that this is, for example, the function sine of g x minus 2 divided by pi of x minus 2. For g is equal to 5, the function is spread out. If I increase the value of g, it is symmetric around the point x is equal to 2, it becomes sharply peaked, and the width becomes extremely small. In the limit of, but the area under the curve is always 1. In the limit of g becoming a very large number, this therefore this has an infinite value at x is equal to 2, but the area under the curve remains unity, and therefore, it has all the properties of the Dirac delta function. So, we have, so the area under the curve is equal to 1 for all values of g, and therefore, we have delta of x minus a is equal to limit as g tends to infinity of sine g x minus a divided by pi of x minus a. So, we just now showed this, that the area under the curve is 1, and it becomes more and more sharply peaked as g becomes large. So, now I have just now shown that if I integrate this, then I get the left hand side. If I carry out the integration on the right hand side, which is very simple, then I will get the left hand side. So, therefore, if I make now g tends to infinity, so if I make g tend to infinity, so the limits will become from minus infinity to plus infinity. So, I have delta of x minus a is equal to so much. So, this is known as the integral representation of the Dirac delta function. So, let me now use this. So, I have here e to the power of delta x minus x prime is equal to 1 over 2 pi e to the power of plus or minus. So, let me take the plus sign I k x minus x prime d k, and the limits are from minus infinity to plus infinity. Now, I had told you earlier that I consider a well behaved function f of x, any arbitrarily well behaved function f of x, and if I integrate this over the delta function, that is, if I multiply this f of x by the delta function and integrate over x prime, then I will get the value of the function at f of x. So, now for this delta of x minus x prime, I substitute this expression. So, I write this down as, please see this, 1 over 2 pi, two integrals now. One integral is over x prime, the other integral is over k. So, both limits are from minus infinity to plus infinity, e to the power of I k x minus x prime f of x prime dx prime. Now, I separate the ones which contain x prime. So, you see this, and then decay also, decay from this. So, I separate the ones from which contain only x prime, and I define a function f of k. I define this function as 1 over root 2 pi, please see this, minus infinity to plus infinity, f of x prime, which is this, e to the power of minus I k x prime which is this, and dx prime. And then what I do is that I then write down that f of x will be equal to, I have taken 1 over root 2 pi here. So, I can write down here 1 over root 2 pi, then f of k e to the power of I k x dk. These limits are also from minus infinity to plus infinity. These two equations describe what is known as the Fourier integral theorem. The function f of k is the Fourier transform of f of x, and this is the inverse Fourier transform. So, in this equation, since x prime is a definite integral, I can remove the prime on the x, and so therefore, I will obtain, I can write down, please see this, I define a function f of k which is defined to be equal to 1 over root 2 pi from minus infinity to plus infinity f of x e to the power of minus I k x dx. Then f of x is known as the inverse Fourier transform of f of k. So, 1 over root 2 pi minus infinity to plus infinity f of k e to the power of plus I k x. Now, the integral is over k. These two equations constitute what is known as the Fourier integral theorem. Fourier, and it is a very important concept in mathematical physics. If I have a plus sign here, then it will be a minus sign here. If I have a minus sign here, I will have a plus sign here. Both are extensively used in. So, this is one of the very important relationship that I have derived. Now, let me give you a simple example. So, let me assume that f of x is something like a into e to the power of minus x square by 2 sigma square, x square by 2 sigma square. So, it is a Gaussian function whose width is about sigma, something like this. This is a f of x function whose width is of the order of sigma. Then its Fourier transform will be f of k will be equal to a over root 2 pi. The root 2 pi is, it should be there. So, then you will have e to the power of minus x square by 2 sigma square e to the power of I k x dx. All limits are from minus infinity to plus infinity. And then we introduce, then we have the formula that we had used, that e to the power of, this is a very important formula that we will be using quite extensively, that e to the power of minus alpha x square plus beta x is equal to square root of pi by alpha into e to the power of beta square by 4 alpha. So, here you can see that alpha is equal to 1 over 2 sigma square and beta is equal to I k. So, you will have, so I will have alpha as 1 over 2 sigma square and beta is equal to I k. So, my f of k will be equal to, as I had written down a moment back, a under root of 2 pi e to the power of minus x square by 2 sigma square e to the power of I k x into dx. So, from minus infinity to plus infinity, and therefore, you will have a by root 2 pi multiplied by root pi divided by alpha. So, that root pi times 2 sigma square beta is I k. So, square of beta, beta square is minus k square and k square, then 2 sigma square by 4. So, k square sigma square by 2. So, this is just a constant, but the main thing that if you plot this function f of k in the k space, then that is also a Gaussian e to the power of minus k square by sigma square, but the width is now 1 over sigma. So, therefore, if a function I had just shown that the f of x has a width of the order of sigma, then its Fourier transform has a width of the order of 1 by sigma. So, if f of x is localized within a distance which is delta x, then f of k will be localized within a distance in the k space delta k, which is 1 over sigma. So, that delta k delta x is of the order of 1. This is a very important relationship, and from which we will derive the uncertainty principle. So, let me go back to my slides. So, this is my integral representation of the Dirac delta function. So, any arbitrary well behaved function, if I integrate by after multiplying by delta of x minus x prime, so I will get f of x. So, then I substitute for delta of x minus x prime from this equation, and we obtain this double integral. This integral is known as the Fourier integral theorem. I can have either of the signs. I can have a plus sign here or a minus sign here. So, what I have just now shown is that f of x is equal to 1 over 2 pi e to the power of plus minus I k x minus x prime f of x prime dx prime dk. I now define the Fourier transform of f of x, and because of its 2 pi factor here, I split it into 2 so that the equations become symmetric, 1 over root 2 pi here. So, f of x e to the power of minus I k x, I have dropped the prime, and then I substitute it back, then f of x is equal to 1 over root 2 pi f of k e to the power of I k x dk. So, this function f of k is known as the Fourier transform of the function f of x, and this is the inverse transform relation, and these two together is often called as the Fourier integral theorem. So, as I mentioned just now, that let me take a Gaussian function f of x is equal to a exponential minus x square by 2 sigma square. So, I substitute it here and calculate its Fourier transform. So, I substitute it here, and here you again use the same relation with alpha is equal to 1 over 2 sigma square and beta is equal to minus I k. So, the square of that is minus k square sigma square by 2. So, we say that the Fourier transform of a Gaussian function is a Gaussian function, and so therefore, this is the function f of x, which is a Gaussian function in the x space, and its Fourier transform is also a Gaussian function. So, what we have derived is that the Fourier transform of a Gaussian is again a Gaussian. The main thing is that its width, something like full width at half maximum, is of the order of sigma, and its half width in the localization of the function f of k in the k space is of the order of 1 over sigma. So, that you have delta x delta k is of the order of 1, delta x delta k is of the order of 1. Now, let me now derive one more relation, that I have this Fourier transform, and I will show that if f of x is normalized, then f of k is also normalized, and the proof is very simple, and we will again use the Dirac delta function. So, I have here, let us suppose f of k is equal to 1 over under root of 2 pi f of x e to the power of minus I k x dx. All limits are from infinity. So, therefore, your f of x is equal to 1 over under root of 2 pi f of k e to the power of I k x dk. Okay. This is all limits are from minus infinity to plus infinity. And if I take the complex conjugate, so f star of x, if the complex conjugate of f of x is equal to the complex conjugate of this equation. So, 1 over root 2 pi f star k e to the power of minus I k x dk. Now, what I want to evaluate is integral from minus infinity to plus infinity mod f square x dx. So, this is equal to f star times f into dx. So, please see this is slightly cumbersome, but very straightforward. So, what I will like to substitute is f star from here, f from here, and substitute it, and then carry out the integration over x. So, now we must be very careful, because this k should not get confused with this k. So, I will quietly put a prime here, k prime here, k prime here, then everything is all right. So, you will have, so if I substitute this f star times this 1 over root 2 pi into 1 over root 2 pi. So, this will become 1 over 2 pi, and there are now 3 integrals, one integral here over x, 1 over k prime, and 1 over k. So, all limits are from minus infinity to plus infinity. So, you will have, first write down f of k prime, f star of k e to the power of I x, then k prime minus k into dx dk prime. Dx comes from here, dk comes from here, and dk prime comes from here. Now, let me then collect all those terms which involve x. This does not involve x, this does not involve x, this involves x, and this involves x. So, I carry out the integration over x. So, what I do is I collect this term, I collect this term, and I collect this term, and carry out the integration over x. So, if I do that, if I put it at the top, then what I will find is 1 over 2 pi minus infinity to plus infinity e to the power of I x k prime minus k dx. This is equal to, I can write delta k minus k prime or k prime minus k, it does not really matter, k minus k prime. So, I have carried out one integration over x, and now what I do is I carry out the integration over k prime. So, I collect all the terms which involve k prime, which is f of k prime, dk prime, and delta of k minus k prime. So, I write this down. So, integral f of k prime, then delta of k minus k prime and dk prime, and of course, this limit is also from minus infinity to plus infinity. So, this is just f of k. So, I substitute it here and I get the relation that minus infinity to plus infinity mod f square dx is equal to minus infinity to plus infinity f star of k multiplied by f of k multiplied by dk. So, that we get the very important relation that this is known as Parseval's theorem, that minus infinity to plus infinity the mod square of the function and the Fourier transform are equal. So, if one of them is normalized, the other will be automatically normalized. So, we obtain the very important relation that that mod f square dx is equal to mod of f square dk. This is known as the Parseval's theorem. So, this is what I have tried to show here. Any arbitrary well behaved function, if I square this and integrate over dx, then the square of that is equal to 1. So, therefore, if this function, if a is such that f mod f square dx, the area under the curve is 1, then mod f k square, the area under that function will also be equal to 1. So, if this is what Parseval's theorem is, that if one of them is equal to 1, then the other one is, this is also known as the normalization condition. This is also known as the normalization condition. Till now, I have done between x and k. There is no reason why we cannot consider a time dependent function and consider its Fourier transform. So, let us consider a time dependent function f of t. Let us consider a time dependent function which I write as f of t and consider its Fourier transform. So, the Fourier transform I define as f of omega is defined to be equal to 1 over root 2 pi from minus infinity to plus infinity e to the power of I omega t dt. This is known as the frequency spectrum, and I will tell you in a moment why this is known as a frequency spectrum. Then the Fourier integral theorem tells us that if I take the inverse Fourier transform, then f of t will become equal to 1 over root 2 pi f of omega e to the power of minus I omega t d omega, minus I omega t d omega. Now, please see this. What is an integral? An integral is nothing but a sum. So, this is a sum over all the frequencies. So, this quantity f of omega is known as the frequency spectrum of the time dependent function f of t. For example, if the time dependent function has only one frequency, then the corresponding f of omega is a Dirac delta function. So, if the frequency spectrum has only one frequency, let us suppose delta of omega minus omega 0, then if I substitute that here, carry out the integration, then f of t becomes equal to 1 over under root of 2 pi e to the power of minus I omega 0 t. So, this is a monochromatic wave. This is a monochromatic wave. So, if I substitute this f of t function in here, then I will get f of omega will be 1 over 2 pi 1 over 2 pi e to the power of I of omega minus omega 0 into t into dt. So, this is the definition of the Dirac delta function. This is one of the definitions of the Dirac. All limits are from minus infinity to plus infinity. So, if a time dependent signal has only one frequency, then the corresponding frequency spectrum is a Dirac delta function, and the corresponding time dependent function is a harmonic wave. So, it is, if I take the real part, it is cos omega 0 t from t equal to minus infinity to t equal to plus infinity. So, you have here, let me consider a simple function. Let me consider a simple function e to the power of minus t square by 2 tau square e to the power of minus I omega 0 t. So, let us suppose that my time dependent function f of t is something like this. If you take the real part, then it will be something like a Gaussian time dependent function multiplied by cos omega 0 t. So, it is a Gaussian pulse of duration tau So, it will look something like this. So, you will have a Gaussian pulse localized within a time interval of the order of tau. So, let me calculate its Fourier transform. The Fourier transform will be f of omega will be equal to 1 over root 2 pi, a I can take outside. So, integral f of t e to the power of I omega t dt. So, I will write it down, integral e, please do this carefully, minus t square by 2 tau square, and then e to the power of I. So, this will be e to the power of I omega minus omega 0 multiplied by t times dt. So, here again I again have the relation like e to the power of minus alpha x square plus beta x, where x is replaced by t. So, my alpha is equal to 1 over 2 tau square and beta is equal to I times omega minus omega naught. So, the evaluation of this integral, these limits are of course from minus infinity to plus infinity. So, this will be, please see this carefully, 1 over root 2 pi under root of pi by alpha, that is under root of pi times 2 tau square multiplied by beta square, that is exponential beta square by 4 alpha, that is minus omega 0 whole square by 4 alpha is 2 tau square, 1 over 2 tau square. So, 2 pi cancel out. So, I will get the frequency spectrum f of omega will come out to be a times tau. This is an unimportant constant factor, but once again the Fourier transform of the Gaussian function is a Gaussian function minus omega 0 whole square by tau square by 2. There is a square here. So, this function is peaked around omega is equal to omega 0, and it falls by a factor of 2 when omega the frequency spread is of the order of 1 over tau. So, the duration of the pulse is of the order of tau, the frequency width of the pulse is of the order of 1 over tau. So, I get this in uncertainty relation delta omega delta t is of the order of 1. This is known as the monochromaticity of the pulse. Smaller the delta omega, the greater is the sharpness of the frequency. So, T tau is something like the what we read in optics as the coherence time. Larger the coherence time, smaller is the spectral width, and this we have all studied in optics. And so, therefore, if you have a very long coherent pulse, then its frequency spread is extremely small. So, let us suppose that I have the wavelength is equal to say 6000 angstroms in the yellow region, 6000 angstroms. So, you will have this is equal to 6 into 10 to the power of minus 7 meters, and omega will be equal to 2 pi times nu. Nu is c by lambda. So, this will be 2 pi into 3 into 10 to the power of 8 into 6 into 10 to the power of minus 7. So, this will come out to be about 3 into 10 to the power of 15 hertz, 3 into 10 to the power of 15 hertz. And let us suppose I have a 1 nanosecond duration pulse. So, the frequency spread delta omega is of the order of 1 over tau. So, this is of the order of 10 to the power of 9 hertz, which is about a millionth of the frequency. So, delta omega by omega is a very small number. So, delta omega by omega will be equal to 10 to the power of 9 divided by 3 into 10 to the power of 15. So, this is about 10 to the power of minus 6, in fact, less than 10 to the power of minus 6. So, it has a very small width and almost monochromatic. So, let me do this again. So, let me have we consider an optical pulse with Gaussian envelope. So, the duration of the pulse is of the order of tau, and the central frequency is around omega 0, is at omega 0. The spectrum, the Fourier transform of this pulse is given by f of omega equal to so much, and if you substitute this here, we have shown that the frequency spectrum is so much. So, the spectral width is of the order of tau. So, this is something like a, let us suppose we consider a Gaussian pulse which corresponds to 1 micrometer wavelength, and it is a 20 femtosecond pulse. So, this is actually the how the electric field will look like, and its corresponding Fourier transform will be very sharply peaked. The Fourier transform of a Gaussian is a Gaussian, will be extremely small, delta omega will be very small, and we will have the uncertainty relation that delta omega delta t is of the order of 1. And we can consider similarly another time dependent function, where tau c, where we have f of t is 0 for all times which is greater than plus half t c or minus half t c. So, tau c is the duration of the pulse. So, this is known as the coherence time, and in between it is a into e to the power of minus I omega 0 t. If you take the calculate the Fourier transform, I leave it as a very simple exercise, it will be very sharply peaked around omega equal to omega 0. In this particular case, I have assumed omega 0 tau c is of the order of 100. So, longer the value of tau c, greater will be the sharpness of f of omega, and greater will be the monochromaticity of the pulse. So, for example, the example that I had just now considered, for omega 0 is equal to 3 into 10 to the power of 15 hertz. The corresponding wavelength is 6000 angstrom. If I consider a 1 nanosecond pulse, then the corresponding frequency width will be 1 over tau c. 1 over tau c is 10 to the power of 9 hertz, and so the spectral purity of the pulse is 0.3 into 10 to the power of minus 6. Now, so I summarize this part of the lecture by saying that if I have any time dependent function or a space dependent function. So, I have f of x, I write its Fourier transform as f of k, and I write this f of k, I define this as equal to 1 over root 2 pi minus infinity to plus infinity f of x e to the power of minus I k x into dx. Then its inverse Fourier transform will be f of x will be 1 over under root of 2 pi f of k e to the power of I k x dk. I can replace x by time and then k with omega. So, that is also possible, and we can take a time dependent function and write down the corresponding frequency spectrum of the pulse. If the function f of x has a localization of the order of delta x, then f of k, the localization is delta k, then in general delta k delta x is of the order of 1. Similarly, I can define for instead of x, as I have just now mentioned, this is t and then this will be the omega spectrum, and if the time duration of the pulse is delta t, then its corresponding frequency spectrum is delta omega, and that is 1. So, this completes. So, you can carry out this with other examples, that you take an arbitrary well behaved function f of x, calculate its Fourier transform, show that if it is localized within a distance of the order of delta x, then its Fourier transform will be localized within a distance of the order of 1 over delta x. Thank you.